developed an open source project to bypass the kernel for networking. We accelerate TCP UDP. Usually we go to banks and other fintech that really care about nanoseconds. Every version is being tested in the 20 nanosecond differences. If there are any problems, we detect them in those resolutions. So usually all those algo trading companies really care about getting the information about a specific stock, and if they'll get it like 20 nano or 30 nano before, they can make a jackpot. So that's our business. That's why nobody had ever heard about the project, because it's for a specific market. And of course, it works very good with Mellanox's hardware. But I'm not going to talk about that at all. I'm going to talk about Valgrind as a tool set for optimizing your code. So recently we started writing a new application, and actually it was C++11, first time that I know about the Mellanox, encouraged by this group. And cross-platform also for Windows, and always when you start a project, you always have like core dumps, and always I use Valgrind as the tool to check it. And all the times when I talk about Valgrind, people always only know about some of the features in it. Usually it's yes, it's a tech if you don't free all your memory, but that's only a small or one feature of it, and it has many more. So I decided to do this small presentation. I thought I can find something that somebody else wrote and just steal it, but eventually I had to write it all by myself. And that's it. Let's start. Okay, great. So this is actually I did learn a few things. So first of all, I always say Valgrind, but it says it's Valgrind. But I will always say Valgrind. I'm just used to it. So, but for you, there might be a chance. So actually, it's Valgrind. And so it's an instrumentation framework for building dynamic analysis code. And it comes with some tools, usually for memory debugging and some more you will see. So it was developed as a master project in Cambridge by someone named Julian Seward. It's an open source, works on x86, AMD, PowerPC, Android, all the Unixes, all the Windows users. I'm sorry, they're not there for you. But I did hear here that you can try running your application with Wine and then use Valgrind. I never tested it, I just read about it. Be happy to get feedback. There are alternatives to every feature in Valgrind. There is a Windows equivalent like Dr. Memory and some others, but I'm not aware of them, never tested them. I'm in Linux. What?
It's not working on ARM at all?
ARM, it does work. ARM is Linux, with the Linux.
ARM is an architecture.
Yes.
It's not
If you take like the latest Windows that can be run on ARM, it won't work.
You talking about Linux?
No, you didn't. You wrote x86. You didn't write.
Yeah, also ARM. Yes. And one of the problems is the overhead, and we'll talk about it. Also, it's very easy to run, and we'll see some examples. So first of all, let's just explain how it works. So Valgrind actually is some kind of a sandbox. It's actually a CPU. It's a synthetic CPU. It takes the code that your application and actually the code that will go into the CPU. So he takes it to himself, and he adds some extra commands and checks and instructions actually for every tool that Valgrind adds specific instructions to where he cares about in the code. For example, if you're running the memory checker, which is the most known one, he will add instructions before the new, delete, free, malloc, and all of those memory allocations. But other tools will add other instructions where they want, where they care. So Valgrind actually is the core that takes your source code, take your binary, not source code, and adds the ability to add instructions in the source code, in the binary level. And it runs it on its own virtual CPU or virtual environment. So all of those tools, each one has what it wants to do. They intercept system calls, and they record information before each call and after, and then they have an understanding of what happened, what should have happened, is it valid or is it not valid, and then at the end, when your application terminates, it prints a log to the screen showing what happened and where's their problems. So Valgrind simulates every single instruction that your program executes. Because of this, not only your code is being tested, also the code beneath. All the libraries are using, if you're using Qt, if you're using glibc, everything that you use is being tested by Valgrind as well. And we will talk about this also. Okay, so what is the goal of the one that we are doing when we are using Valgrind? So maybe not all of us will admit it, but C, C++ are very difficult language to write code from. I'm coming mainly from Python maybe, so it's like C is hell, C++ the same. Even worse. So most of it is because you're not in this protected land of the virtual machine, that if you are Java or C# or Python, you are in charge for the memory management, for the resource. It's much harder to write code. It's much easier to write code in Java, Python, and C++. It's much harder. C and C++ has a lot of undefined behavior. You read, if you'll do malloc and then deallocate the memory with delete, it's undefined behavior. There are a lot of undefined behaviors that you need to. What will happen after? You don't know. It's just going to be undefined, and God knows what will happen. So a lot of undefined behaviors that we need to fix and find, and it can be different between different compilers. Bug can happen because of uninitialized values, and debugging it can be very frustrating. It can take hours. You can read a non-allocated memory address, or read a memory after it was freed, but it was never, it would be called free, but it's still there. So it really depends on the stress of the system to have a bug. So a lot of those stuff are very hard to find. Besides memory, there are other resources that you must close after you don't longer need them, like file descriptor sockets. If you won't, we have a bug once that we didn't close the sockets, not sockets, files, and at the end we blew up because we tried to open files, we never closed them. At the end we got to the limit and boom. But Valgrind, it's not only a debugger, it can help us find deadlocks. It's also a tool that can let us do a performance check for our application. And it can also show us the memory usage and show us like a graph. We'll see that. Let's talk about the limitations of the tool. So, if 2 weeks ago we had a two months ago we had a presentation from Pyrosoft, or some of us know CPP check. Those are static code checks. Valgrind is a dynamic checker. If your buggy code is not running, you're not going to find an issue. Now, dynamic checker is better from a static checker. I'm going to show you I'm going to show you some code snippets here. Some of them our smart compilers will identify, but at the end, compilers are not smart enough to identify all the bugs that we write. That's why we need a dynamic checker. And static checkers are just not good enough, and frankly, I don't think they will ever be perfect. They're good, so I recommend using them, but we always need the extra layer. So what else? Problem or limitations? So another thing is that if you're using other libraries, so as we said, Valgrind will warn us also about issues found there that we don't really care about. or we care but we can't really do anything about it sometimes. So we just can have false positive or real errors that we don't care. Like let's say that we had in Mellanox we had a simulator that had plenty of bugs, but because it wasn't the main product, we didn't really care about it. So we just cared about something running above the simulator. So this is like an example that you're running above a library, you know it works, you know it has issues, you don't want to know about it, you only care about your product. But there are ways to ignore this. Valgrind can't detect out-of-range reads or writes to stack or global arrays, only dynamic. If hardware is involved, here in Mellanox, of course, if hardware is involved, then Valgrind cannot know about it. If let's say there's a hardware that maps a memory and you write to a socket and the hardware will write to that memory, Valgrind will say, hey, this is uninitialized memory, what are you doing there? And it doesn't really know that the hardware wrote data that is valid. But there are ways to get around this. Also, another thing is Valgrind is very slow, obviously. So you cannot, first of all, you cannot run your code always with Valgrind, it's only for testing purposes. But if you have tests that expect a certain response time and Valgrind makes it run slower, you can have timeouts, let's say, and then valid passes will not be chosen in your applications, and you need to take it into consideration, like some kind of defined debug. And when you're debugging with Valgrind, let's say waiting for a response from a socket or something, you will wait 50 times more. So you will check all the valid code and not go into the timeout ifs else in the codes. So what is needed in order to run a Valgrind? First of all, it should recommend it that it's a must to compile with debug symbols, or you won't understand all the logs. Just going to show up as a question mark. Not smart. I did read in the manual, it was a new tuning that they recommend for memory to compile with 0. I never did it. I always used 02, 03 and it always worked. Maybe we have hidden bugs in the code. I didn't find any, but this is what the manual said. I'm not going to say differently, but I never did it. That's it. That's actually one of the nice things that, contrary to other tools, you don't need to debug your application differently. You can just debug it, just compile it with debug symbols and you're ready to go. For basic run, just run Valgrind without the capital V, of course. Thanks for PowerPoint. And your application names and your application arguments, and that's it. The basic tool is the memory analysis tool, and it will run right away and print to the screen all the output. Just one thing, let's first talk about flags, the general flags, and specifically for the memory. So a log file, much better than just running without, so you can have all the log in one place. So just a log file to put all the information. Track children. If you are running executable, you're forking a new child, not with fork, but with the exe system call, then Valgrind will track also the child. Sometimes you want it, sometimes you don't want it, depends on you. By default, it's no. Track FDs, track non-close file descriptors. At the end of the application, you're supposed to close everything, basically. Suppression is a suppression file. Read var info, which prints more precise error messages in some situation. Track origin, it's very useful and very expensive in time option. What it does, if you're using an uninitialized value, it will tell you where it came from, because sometimes we'll talk about it. Show mismatch freeze. It reports if you allocate with new, but free with free, or vice versa, or delete and delete with brackets and all of those. Show the kinds. For this, we have this slide. So basically, there are 4 kinds of memory leaks when in Valgrind perspective. There is the definitely lost, the indirectly lost, the possibly lost, and the still reachable memory. So we'll start with the definitely lost. Definitely lost is definitely lost. Like what it says, it means that there is no pointer in your application in the end of the run. There is no pointer that points to this data block. That there is no way that your application could free this memory, and that you have a bug. That's what it means, and that you need to fix it. That's also what it means. So this is like 100% bug, and you should always fix those. So this is the definitely last one. The indirectly lost is something a little different. What it means is that you have a pointer that you're leaking memory in a pointer-based structure. So the basic example that they give is that you have, like, let's say, a binary tree, and you just lost the root pointer, but so the root pointer is a definitely lost. But all the sons, all the ones beneath the root, you have a pointer to them. If you would free the root, you might have freed the other ones. A better example for C++ maybe is you have a class that holds pointers. You have class A that has pointers to other classes, and you lost the pointer to A. So of course you cannot free all what's inside A. So A is considered as a definitely lost, but all the pointers inside A are indirectly lost. Because when you will fix the structure of A or delete it, then hopefully B, all the pointers inside A will be deleted as well, or they will be definitely lost. That depends already in the logic more inside. Another kind of leak is possibly lost. Possibly lost is means unless you're doing something unusual with the pointers, such as point example is the middle of the allocated block. So a lot of applications sometimes they allocate like 1 mega or 5 mega in order to work faster. They allocate a big chunk, and they divide it in the application level to small chunks. So in this way, when the application closes, you might have a pointer to the middle of the chunk, but somewhere you know the offset to the beginning of the chunk. Now, why is it important to know the offset is the beginning of the chunk? Because you cannot free it with a pointer to the middle of the chunk. If you will give free a pointer to the middle of the chunk, it will be undefined behavior. So also possibly lost is something that you should look about. Sometimes, a lot of times actually, it can just be a bug in your application. So it's worth looking on. The fourth kind is, we can discuss it's a bug or not, but it's Valgrind doesn't alert about it usually, and a lot of application has this. It's still reachable memory. So in this leak, and I'm saying a bit like this because it's not really a leak. When the application exit, you had the pointer to this memory block, but you didn't free the block. So on principle, you could have freed this memory, but you decided not to. Now, it's a legitimate decision not to free the memory when the application exits, because 1 millisecond after, the operating system will come and destroy the hell out of this section in memory, so who cares? So there are a lot of applications, usually like small scripts that go up and go down, that don't bother freeing memory, and that's legitimate, and there are a lot of frameworks or stuff that do that, and Valgrind by default doesn't warn about it. You can, with the show-leak kind, all see those stuff, and if you care about it from some reason, you can handle this.
All these are detected at the end of the run? Or
Yes.
Okay.
1 second. If in the middle of the run of your application you forgot pointer, then Valgrind will write it to himself at that point of the time. But still reachable, he will not know about till the application exits.
Okay, so this is what I'm missing. It's not Java or C# where all pointers are actually tracked. The pointer is not a special kind of memory. It's just a value in a memory cell which contains an address, which can, in native languages, we can copy or do whatever we want with it, how to track it. If I just put it cast it to if it's 64-bit, cast it to 32-bit values, copy them somewhere, and then I can join them later to create a. How can track it?
How can you track that you have no pointer to this place?
It sounds like it can't.
It can.
From my knowledge of C++.
I know that he tracks, he uses his own malloc and free, and I know he has access to all your pointer and stack, so he has a way of knowing if you did some kind of games. He knows that you have a pointer, he knows every pointer in your application where it points to.
That's what I mean. There's no such thing as every pointer in your application. Just the entire memory block of the application. You can put it anywhere as long as you know how to access it later. So I don't see how it's feasible in C++. Maybe if you don't do anything, if you go really straight by the book and you copy it to some, it doesn't even know type because it doesn't have source code. So I really don't know how we can track it. So
It knows. Well, I'm not smart enough to answer this question, but the people who wrote this are smart enough to do it, and because they are aware of all your code and you are running under their CPUs, they do know all your pointers and all your games, and no matter what you do, they will know if there's a valid pointer to this memory block in your application.
How are you tracking data flows?
the return value, and then you see where it's copied every.
You have an emission allocation, and then you might copy that pointer value around.
They do.
By replacing the heap and monitoring everything that goes on with the heap, what you've basically done is you've put in what a Java virtual machine does.
If I have something that shifts the value and put it somewhere, then I can shift it back because it's comfortable, because it's I store pointers. Store pointers, for example. I really don't see how.
If you XOR your pointer, if you XOR your pointer,
yes.
And I guess maybe Valgrind would think you don't have a valid pointer to this location, and this is correct. And if you have, before you exit, you XOR it back, then you're a very weird guy, and maybe
there's actually a very interesting data structure for a doubly linked list that uses a single pointer, and you can reverse the list with one operation.
Okay, so
because of the XOR pointers.
Valgrind has false positive, false negative, and it does sometimes do mistakes. As long as you're a regular user, usually don't doubt what it says.
So if you track if I copy the address that's somewhere else?
This of course.
Yes,
Goes without saying.
know that anyway.
What?
The compiler should know that by the
Way
hardware.
after the compiler, it runs on binary. It does instrumentation on something that doesn't have your software.
No, but it knows how to read the binary. You run on Valgrind. It's like running Java code.
It
Like
has
Java knows when to
information.
free your memory. It's the
It
same.
has debug information. That was the first requirement.
So that information is simple, it's not everything. But okay.
I challenge you to
What about the cyclic pointers?
what? Cyclic pointers. It will just say that you didn't free them. Oh, it might list them as
Doesn't comply
still
with any of
reachable.
the terms. It's not definitely lost because every item has a pointer. And it's also directly lost because, again, every item, if they keep an internal data structure, which it has to be a DAG, like a directed graph. And if it sees a separate component, then it knows you have a disconnect.
Yes, cyclic pointers doesn't mean that.
If there are two objects that points to each other, I guess it will consider it as still reachable. A lot that points to each other. Like a cyclic graph that only points to itself.
It doesn't matter as long as the memory's got to be allocated. Who cares if you have a pointer to memory that's already been allocated? That's not loss.
In any case, if you have a pointer, if you have a cyclic graph that is connected to your stack, I mean the pointer that is on your stack currently, which means it's not linked.
You need to have a pointer to one of those cyclic from the outside. How do you get into this cyclic? How do you go into this cyclic thing?
But the tool doesn't know what I I'm going to do with the pointers. Just
Yeah, but he
see
knows.
if there whether there is pointer or not.
So the main pointer to the cyclic or
Yes,
cyclic will be the main. You need to have a pointer to the head of this cyclic, right? Somewhere you need to go inside. It cannot be connected to himself, and that's it. So
that's
it will be definitely lost, and the rest will be indirectly lost. I think we can check it later. So let's just look back. All of those examples here are very dumb, stupid, and that's the point. Because I'm not going to show you. I cannot show you like thousands of lines. Usually the Valgrind bugs are easy to fix, just hard to find. So this is very obvious. We have a function main that calls function run. Function run allocates an array, magically forgets to delete it. Pay attention that if this array was allocated in main, it wasn't yes. Was still reachable because it was reachable from main. By moving this to a different function, and now calling it definitely lost. And we have a very nice debug message that says that in main, in run, we used a parameter new, and we have 40 bytes in one block that is definitely lost already. And each Valgrind has this is the format of the log. It supports also XML. For whoever cares, and on the left side it shows you the PID. It's good for if you're running if you have a executable that has forks and has more children that has different PIDs. It's better. It's easier to understand what's happening.
Is it possible to see the file and line number?
Yes, it shows it. It shows the file and number. Here it doesn't show because it's. I guess I didn't do a good example from something. It shows. I don't know why it doesn't show here, but it shows. Of course, it shows. We'll see in other examples. You'll see it shows it. Invalid right. So this is actually very the same example. Yes.
If you do delete this location, but with the wrong delete type,
we will see it. It will. If you will delete it, it's free. Let's say.
No, delete.
Delete was delete, and it will also warn you about this. We'll see an example of this also. Another type of error is invalid write. So invalid write happens when you write data to places you're not supposed to. So maybe that's the most obvious option, but also just randomly choosing an address space of when writing there, it will be the same effect. Every place you're not supposed to write to the memory, it will tell you about it. Some of those will crash you, and some of them will have undefined behavior. Also crashing. Technically undefined. Yes, also crashing.
You might be lucky and it crashes.
Yeah, if you're lucky, you'll be crashed. Yes, exactly. So here we're
crash sometimes.
Yes,
yeah,
it depends.
If you're lucky,
yeah, but it can change between runs.
Of course, between run, environment, CPUs, everything. Compilers. So here we're writing to an index that is not valid, and of course we get a memory. I have no idea why I don't have line numbers here, but there is. For sure there is, and we'll see next one that has it. So here also we have an invalid write of size 4, because this is an integer. We're trying to read the 4 bytes from a place we're not supposed to, but also Valgrind tells us that this is zero bytes after a block that you did allocate it, meaning that he knows if this is like a random place, is it a place that you allocated before, where did this address came from?
Is that going to detect things like this that are a very short distance after the allocation block, or if it's very far away, it's going to find that too?
If it's 10 mega after, I don't think it's going to tell you you're trying to read 10 mega after you allocate it. It's just going to tell you you're trying to read invalid write in this address. I don't know exactly to tell you how close you need to be to an allocated memory in order for it to tell you that it was allocated by you. I know that it does hold lists of all the allocated and free sections of the code, and when you are doing an invalid write close to where you allocated, it does tell you about it. So it helps you understand. Yes?
It's a bit complicated. Let's say you had another allocation right after this one. And you still have this erroneous piece of code because you're definitely out of bounds of ARR. But you could be trying to access a legal address from the program's point of view, but clearly be a bug. So you wouldn't call them in this case, but it would be a bug that you want to know about.
Every access to out of range address will be detected. Even every one of them
It's
will
not
be
just
detected.
about allocated addresses, but it is about checking the ranges.
Yes, even if you just, like I said, if you just decide to do, I want to read what's in FFF123, you will, if you will lucky enough not to crash or yes to crash, Valgrind will tell you about it.
Even if that address happens to point into
No,
an allocated block?
No, if it's an allocated block, you won't tell you. It won't.
I think that's what he was asking.
So he won't tell you.
So it might protect you against core dumps, but not necessarily against memory corruption.
It doesn't check for
buffer overflow.
It does out of range. You're saying that.
I think it can, because you don't actually allocate on the machine.
You can check for it, yes. No, base pointer, you can locate size, you can go for the access.
So when you access it, you access it for the original.
You access with one array to a different index, but it will fall on an array that was allocated after.
Yes.
You're assuming the.
Who said that they're allocated after?
Let's assume
It's like you allocate twice, then you take the
Yes,
difference
yes.
between the addresses, and you add that to the previous one.
So
allocation is not one.
I'll tell you what Valgrind does. Valgrind has I didn't go into technical in this slide, but Valgrind maps all your memory with something he called V-beats. And this is specific beats that Valgrind identify. In the second you're trying to read something, now every time you allocate memory, he writes it himself. This is not a V-beat anymore, and every time you free it, it goes back to be a V-beat or something very similar to that. So if some kind of not magic, or you're doing some memory games and you fell into the V-beats that you didn't allocate, Valgrind will tell you about it. If you got to this very cool pointer games that it works, Valgrind won't tell you about it because he knows all the blocks that were used. He doesn't look by the pointer; he looks by the address. So if you have two arrays and you go with one variable to the array of the second one, it will not warn you about it because it checks the memory itself, not the pointer.
You won't get buffer overflows unless you're lucky enough to try to access an unallocated address.
If you will try to read or to write, he will tell you about it. If you will just move a bad pointer from place to place, and we'll see it, and you're not going to read or write to it, no. But your application is not undefined in a situation like that. Because you hold a pointer to a place that is not valid, but you're not really doing anything with it. You're just holding it. Okay, and this is actually very similar to your uninitialized memory. The next slide. So, invalid read. So, invalid read happens when your application reads from places it's not supposed to read. So, a very common use case maybe is that you allocated something, you delete it, and then you try to read it again. And it might work because maybe it wasn't really deleted yet by the glibc or whatever allocator you're using, but it is considered undefined behavior, of course. And Valgrind will tell you that this block was allocated somewhere in this line. It will tell you the line. It was deleted somewhere here, and you're trying to read it over there. So he will tell you about those. And of course, if I wouldn't do the problem is here is in the line of the printf. I'm trying to print it. Okay, and syscall params points to uninitialized bytes. So here we see actually this is, I didn't really run it especially for this presentation, so you do see that there are lines of code. I think all the old examples, because maybe it was like 5 lines, Valgrind didn't detect it, or because it didn't write the line numbers, but here this is like from our project, so you see that it does tell you the file name and the line. So this is what you will see in your basic run, not what you saw so far. So here, this is actually an example from the libVMA. What we see, I'm not going to go into very big details. It uses epoll, and in order to do epoll, you need to pass a struct called the epoll event. An epoll event has unions and all sort of data, and you pass it as a system called the epoll control. And it turns out that this piece of code doesn't initialize the entire epoll event struct, only part of it. And this might cause issues in the epoll control because it's undefined behavior.
So it detects this only because epoll control actually tries to access the uninitialized fields.
So
it's not like a static analyzer that knows beforehand.
Every system called Valgrind has a piece of code that checks the struct before and after. I'm not really sure if this checker of system control checks that all the fields are defined, or there is some kind of orders that the system control first read this and that. I can tell you that this piece of code worked, meaning that without Valgrind, checks will never find it, and maybe it would keep working till someone in the Linux will, let's do the logic of system control differently, and then boom, it would crash in some weird Linux distribution or something. And actually to fix it, like most of the Valgrind fixes, is like online. It's easy as that. The hardest thing is maybe to find it.
The chance your compiler is doing this for you.
Maybe. It shouldn't. It shouldn't because it's a syscall.
Yeah, it's a syscall.
It shouldn't do it.
Yeah, you're right.
A conditional jump or move depends on uninitialized values. So here we have x and we print it. And print inside what it does, IO printf. The printf, of course, when it tries to print the string, it reads x, and then because you never initialize it, it's considered undefined behavior. So it's important to understand that your application program can copy around junk or uninitialized data as much as it likes. Memchecks observes it, it's keeping tracks of it, but it will not complain about it. It will only complain when your program attempts to do anything with this uninitialized data that may affect the program externally visible behavior. Let's say in this example, X is uninitialized, memchecks observes it, but it doesn't tell you anything. Only when it goes to IO printf and then to IOV printf, then the comment is made, because the IOV printf has to examine the value of X. But if you will just use X and never examine it, you will never get a warning, an error by Valgrind, and that's okay because it didn't do anything undefined.
Did I understand from what you said earlier that Valgrind only checks for errors that are in the heap and not in the stack?
I did say
because in this example is in the
no.
stack.
I only talked about out of range. If you have a global array, it won't find mistakes there. But uninitialized value, you will find.
By the way, how exactly can we find it in the stack? What if you're on the stack of an object which has been placed on the heap?
No, because it creates its own stack. It has malloc.
We will talk about that Valgrind can actually detect global and static. A lot. Okay, so this answers your question about invalid free. So invalid free can happen when you double free something, or you deallocate with free something that was allocated with new, or delete with brackets, and it's just very, you can just see it that something was allocated with operator new with bracket, but we used free to free it. And just a reminder to everyone, a friendly reminder, if you allocate with malloc, calloc, realloc, valloc, memeline, you must use free. If you use new, you need to deallocate with delete, and if you allocate it with new brackets, you need to delete with delete brackets. Everybody uses the huge pages.
I use it once, a long time ago.
So I use it a lot. Valgrind doesn't detected errors over there, so you should have
I wrapped it in an allocator.
I
just stuck it into STD bucket.
Okay, maybe next time we'll talk about huge pages. But it will point you a warning about this, that we don't support huge pages. Another small things. If you are doing mem copy when the source and destination has an overlap, also considered undefined behavior, and some of those mem copy start from the end of the memory blocks, or really, I don't really know what will happen. So undefined behavior, mem copy, str copy, str cuts, blah blah blah. This actually I had an application I saw like 2 weeks ago. I saw an application that tried to allocate 1 million, I don't know, trillion memory, and I got a Valgrind. We're trying fishy values. So also negative or very, 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 very big values will also get something. Suppression files. So as we said, if you're doing something very sophisticated or you have hardware, you need to use a suppression file. So very quick way to do suppression is just run your code with gen suppression all. It will generate a suppression code for you, and then you can just filter out all the really good suppression or not. You also have a wildcast. You can just skip. This is how does the suppression is written. So the first line is the title. You can just write the description, and when the Valgrind finishes to run, he will just tell you I had X of those suppressions that I ignored. Then it has the type of it. If it's a definite loss for memcheck, for undefined, it will uninitialize, it will tell you something else. Then it can just show you the trace of all the functions, objects involved. You can just use 3 dots and ignore it, or put a full trace. Depends on what you want. Like in this example, all the functions that has memcheck value 8 that go through this function, LDMA get devices, we don't care about it. Besides that, you can, in your application, put macros and compile with Valgrind and tell Valgrind this memory is fine, it's initialized. Of course, this is the macro. Valgrind make mem undefined or defined. You give it the pointer and the size, and then he knows that this memory is okay. This is a small code snippet. We query the hardware about something, and we tell Valgrind this entire thing is memory defined. No problem. Don't tell us about it. There are more sophisticated macros. I never use them, but you can invoke memory, run from your application in certain times. Some use cases that are there, you can use them. Those macros should only be under if-def or something, because they slow down the run of the application, and they force you to compile with Valgrind devel, something that you don't really want to do all the time.
Wait, the macro forces you to?
Yes, this macro is defined in Valgrind.h, so you have to compile with it. If you're cloning the code and you don't have Valgrind installed in this machine, the make will fail. So usually what the project has, they have like a Valgrind.h inside that has under if-def, and in the configure of the automake that nobody was supposed to use, or the CMake, you can do with Valgrind or not. And then if you do with Valgrind, it will tell you, oh, you were trying to use Valgrind, but you don't have the package Valgrind devel installed. So that's it. So those macros are defined in Valgrind's H files. So now we'll talk about the less known common and less known tool in Valgrind. So we'll start with the SG check. So SG check is an experimental tool that finds overruns on stack and globals arrays. What we just said that Valgrind doesn't know how to find, so he does. This tool is not perfect, experimental, with an explanation how he does it. It won't find anything, but it's better than nothing. Valgrind. So Valgrind is a Valgrind tool that detects synchronization errors in C, C++, also Fortran. All the programs that use POSIX pthread primitives. It detects misuse use of API, potential deadlocks, and data races. If you want to use C++ threads, you need to do an effort. There is another tool that makes the job easier, maybe. It doesn't recognize atomic and futex. Really, it's more for C guys on Linux, I guess. It's very slow, like the entire Valgrind. It's very slow, but it helps. It's very good. API misuse. So if you're trying to unlock an invalid mutex, or unlock a non-locked, or there's a whole list, it will just tell you about it that you're unlocked and non-locked lock, and which is undefined behavior as well. Deadlock. So this actually has a definition of deadlock. The deadlock is when you have a resource that has two locks, then all threads must acquire the locks in the same order. If one thread acquires lock A and lock B, and the other thread will acquire them in the opposite lock B and then lock A, there might be a deadlock in that point. Now, those bugs are very hard to find because you can have thousands of runs and it will never happen, and at the end it will happen to the client on a Friday night and you will never understand what happened. And Valgrind, what's good of it is that he just writes down for each lock the order of it, and he builds a graph and he checks, and if he finds that there one place in the code that you get the resource with lock A and lock B, and another place that you use the locks in a different order, it will tell you about it. And you don't need to catch this, you just need to run the buggy code. You don't need to have a deadlock by Valgrind in order to find it.
Does it have the general case?
Of what?
A graph bigger than 2.
Yes, of course. So this is just explains what I said about the graph, and this is how the message looks. So there's an acquisition issue, it violates. Here it was acquisited this way, and over there it was acquisited the other way. Datarace. So datarace, you have something that's supposed to be under a lock, which is not under a lock. Now, sometimes you have let's say we have in one of the applications in Mellanox, you have a thread that every 10 seconds he reads the log verbosity in order to increase it or decrease it. This is not under a lock, because so nothing will happen if in this 10 seconds the log verbosity will stay lower, and only in 10 seconds it will increase. So all those messages are legit, but some of them you can ignore. So it's fine. But every resource that is common to a few threads, and you reach it from different threads without a lock, he will tell you about it. If you decide to fix it or not, it's your fault. Your decision. DRD is an experimental thread analyzer. It's very, very similar to Valgrind, but it's still considered experimental. It does everything Valgrind does. It has some more extra analysis tools. You run it with Valgrind -tool DRD. Those are two minuses over there. You should first do regular Valgrind, clean all the memory issues in your code, or it will not work properly. It has better support for C++ and Boost threads. So if you're using C++, like you're supposed to, because it's C++ conference, then you should use this tool. What's good with this tool? It find lock contention. So I don't want to sound like a whole argument. I'm just going to say basically locking is not expensive. The lock itself, like the system called lock, is not expensive. It's more expensive than other things, I guess, but it's not like super expensive. What's expensive is waiting on the lock, or you have a lot of threads waiting on the lock. So a lock that is being fought over can cause serious degradation in time-critical applications, like we have, but other time-critical applications as well. Of course, identifying those areas is only the first way to solve the issue. Even if you do know that there is a certain lock that you have a fight over, it doesn't mean that you can. This is the first way to solution is identifying the problem. Maybe you need to redesign the code, some other, maybe not use threads, maybe use a queue somehow, synchronization, but it will help you identify that there was an issue with this lock. So there are two flags, exclusive threshold and shared threshold, and it will tell you, for example, that this lock mutex was held for 503 milliseconds, and you did put a threshold of 10 milliseconds, but take into consideration that the entire program runs slower. But for time-critical application, it's good to know those hotspots in order to take care of them. Massive heap profile. So this tool measures how much heap memory your program used over time. It includes both the use space by and the extra for the bookkeeping and alignment. And also can measure the stack.
What's that fragmentation?
I think not. Not true. It's good for testing long-running application to verify you don't forget to free some memory, and just think about a map STL that just keep adding stuff to it and never delete. Eventually it will explode. You will have no leaks, but the memory usage will go up and up and up. It's important to note that Massive not only tells you how much memory your application used, but also gives you the locations of every percentage where the memory was allocated. So even after so for each data point in your application, you can see how much percentage of your code was allocated in what places. So running it also the same, -2 massive and the arguments. Usually it writes it to a file called massive.out.pad, which is good if you have children that you have in your application, or you can just use the massive out file parameters. And there is a utility called msprint that creates this thing. So what we see here, every run of your application, Valgrind massive, it does a snapshot. In this case, we had 94 snapshots. The double dot that you see is a standard snapshot. The strudel one is a detailed snapshot, and the peak, the
consumption. The hash?
So the hash is the peak consumption maximum that was used. So this application just allocates lots of memory at the start and finish. But of course, there's a much nicer graph that goes up and down and up and down. And this is a more detailed. You see this nice ASCII of percentage that 88.9 was allocated here, 22 was allocated here, and you can see for each snapshot how much memory was used. Fascinating. CoreCpp. So CoreCpp is a profiling tool. It records the call history and manufacturing in your program. Collected data consists of number of functions executed, the relationships, a caller-callee, optionally at the cache simulation and branch prediction. We'll talk about also. Basically, I just showed you how it looks in the GUI. Didn't go deep into this tool. At the end, when you have an application that you want to, it can be your application or something else. Maybe the first thing you want is like a general overview of which function is being used the most. So here we can see this big rectangle in the middle, which uses 34.5% of the memory, and this is the function of the CPU, not memory. And if you want to optimize your application, this might be a good place to start. So if you have a very big application and you start optimizing all the control paths or maybe the configuration reads, you're not going to optimize that because it only happens once. So you need to find where's the data path, where's all the what code is being run the most in your application. So this is the place to start. CashRun. So CashRun is cache and branch prediction. So CashRun simulates how your program interacts with the machine cache hierarchy and branch predictor. So I will just say it is a synthetic CPU, so it's not it's not taking into consideration other processes or kernel processes, but it is good. There are other tools for the Linux guys. I guess maybe the best one is Intel Vitune, but it costs a lot of money. You also have perfs that comes with Linux, and you also have this. All of them can be used. Usually they all show the same thing more or less. I did check it once. It shows you cache read of data and instructions and misses and writes and conditional branches that were mispredicted. You can change something small in your application, run it again, and use the CGDiff to see the difference between the runs, and knows how and understand what the small diffs did. It's hard to understand the cache, I think. I will talk about it in a second. This is the output. When you do CashRun, you should run it. You should compile it with the default optimization that you do, and you should do debug signals, of course. You can do a few runs and use CG merge to run the results together, and then it will just show you for each function instructions read, misses, read misses for every function. But I think a better view is this. For each line of your code, you can see the read, the miss, and then you can really understand in the data path how much each line costs you, and maybe understand if you can optimize it somehow. So I'm not going to talk about improving the app a lot because this is like a different subject and we can talk about it for a long time. So line by line are very useful. It's a good place to start. You can measure the instructions and see how much time, how much line took, how much each time look took. So L misses are typically much bigger source of slowdowns than L1 misses, so it's usually worth looking at those. Any snippet of data misses, read or write also counts. If you find any, it's still not always easy to work out how to improve it. You really need to understand how the cache works. A lot of times in our application, I can give you a lot of weird examples. Like I had a few members and we put them in a class, and then inside the class there was a 30 nano differences. Instead of putting them inside the class, we had a class A, which had three members. We put it inside the class inside it made differences in the code. A lot of times the code shifts and it goes out of the cache. There's also the size of the class. If it's a line to 64, there's a cache line. There's a lot of stuff to take into consideration. But it can give you a clue that this line might have something that needs to be fixed. Thanks.
Thank you.